Okay, so I welcome all of you again to this class of MEC 551 Thermal Engineering. Okay, so today we're going to discuss something about air conditioning. So in the previous class, we discussed something about refrigeration cycle. Actually, air conditioning and refrigeration cycle, they work hand in hand. Okay, so again, regarding the assignment which was given to you, you will need the knowledge of air conditioning and then refrigeration cycle. So I'm thinking that after I finish this particular chapter, then I'll explain some of the important areas in the assignment to you, because I discovered that some of you have started having problem. Okay, so by the time we will finish discussing this particular topic, then maybe things will become clearer to you. Okay, so and in air conditioning, what is the definition for air conditioning? Okay, we all know in our normal daily lifestyle or daily activities. Okay, so we try to sometimes, when the weather is too hot, we try to sit in an environment where the environment is relatively, the temperature is very good condition. Okay, so moderate temperature, and then the humidity, the air distribution is good. Okay, so classically, air conditioning is the treatment of air in order to simultaneously control the temperature of the air. Means if the temperature of the air is too much, we need to bring it to a comfort level. And then the humidity also, and then the cleanliness, and then the distribution finally. Okay, so but there are four main purpose of air conditioning. One of which is the heating process. Okay, so one of the main purpose of an air conditioning is for the heating process. And then we also have cooling process. Okay, so I will go into details about these particular areas. And we have also humidification and dehumidification. Okay, so these are generally the four areas that in any air conditioning application is used. Okay, so in which areas is air conditioning mostly needed? In offices, residential areas, in your rooms, hospitals, even in classrooms also, the air conditioning application is widely used. On the automobile industry, in the aircraft, also air conditioning is very, very important. Okay, so now air conditioning is meant to provide comfort zone. When we say comfort zone, a temperature which is not too much cold or too much hot. So a comfort temperature, and there are three main factors. Okay, that depends on the comfort of a human body or the comfort zone. And these three factors are the temperature, humidity, and then air. If the temperature is extremely high, you will not feel comfortable. You will feel discomfort. So you tend to sit in an area where the weather is cold. You understand me? So also, if the temperature is too cold, maybe 10 degrees Celsius, 11 degrees Celsius, or even minus degree, then you will not feel comfortable. So the comfort level for any human being, okay, is given by this, as far as temperature is concerned. Also, the relative humidity, also supposed to be between 40 and 60%. And we have the air mass or the airflow, okay, the velocity of the air. There should always be ventilation. If you find yourself in a room where the window is closed, no fresh air coming in, again, you will not feel comfortable. You understand me? So other factors, okay, air cleanliness, the odor, radiance, and so on and so forth. Okay, so now let us look at atmospheric air. When we say atmospheric air, typically air consists of so many components: nitrogen, oxygen, and small amount of other gases. Okay, so we will not go into these chemical details. Okay, so now air in the atmosphere normally contains some water vapor. You see, if you take any sample of atmospheric air, that sample of atmospheric air will contain some amount of water vapor. You understand me? Okay, so air that contains no water vapor is called the dry air. So basically, atmospheric air consists of two main components. We have the dry air component, dry air, and then we have the water vapor. Okay, these are the two main components of atmospheric air. As far as our thermal engineering is concerned, we are not interested in the nitrogen, oxygen, or whatever constituent. We are only interested in the dry part of the air and then the water vapor. Okay. So now the temperature of air in air conditioning application ranges between -10 and 50 degrees Celsius. Somebody will say, why? Say, -10. I'm saying the application is -10 and 50 degrees Celsius. So -10 is extremely cold. Okay, so here, when we say the air conditioning application, we are referring to also refrigeration cycle. Okay, we are not referring to human being, the comfort level of human being. The comfort level of any human being with respect to temperature should be between 22 to let's say 27 degrees Celsius. But widely speaking, air conditioning application, okay, the temperature ranges between -10 and 50. So -10 because maybe if you are working in a pharmaceutical industry, so in pharmacies or pharmaceutical industries, they need to preserve certain drugs at a very low temperature. So also, and so it means that air conditioning application will be needed also over there. You understand me? Or let's say if you are working in a textile industry where you produce clothing, shirts, camis, and other things. Okay, so in the textile industry, normally when they pack the clothing in the warehouse, they need to raise the temperature in that particular room a little bit above the ambient temperature so that animals, creatures, insects will not attack and destroy the materials. You understand me? So air conditioning application has a very wide range in terms of temperature. But when we talk of comfort level for human beings is between 22 to 27 degrees Celsius. So now we are saying that dry air can be treated as an ideal gas. Okay, so what is an ideal gas? An ideal gas is a gas that obeys the law PV equals to what? MRT. Okay, so what we are saying over here is that, like I've told you, atmospheric air can be divided into dry air and water vapor. So, but we are saying that the dry air that is present in the water vapor, in the atmospheric air, is considered as an ideal gas. And if it is an ideal gas, then it means that its specific heat capacity will be given by 1.005 kilojoules per kilogram per Kelvin. So that is the CP for dry air. Okay, 1.005 kilojoules per kilogram per Kelvin. Also, the enthalpy of any ideal gas is given by the specific enthalpy of any ideal gas is given by Cp times the temperature of that ideal gas. Okay, it's the specific heat capacity times the temperature of that ideal gas. So we are saying that taking 0 as the reference temperature, the enthalpy and enthalpy change of dry air can be determined from, so the enthalpy of dry air component is this, and change in enthalpy, assuming an atmospheric air is undergoing a change of state from state 1 to state 2. So the change in enthalpy, which is delta H, will be equal to H2 minus H1. Okay, so which is given by Cp into bracket delta T. You understand? Okay, so now let's proceed. And now we are saying at 50 degrees Celsius, the saturation pressure of water is 12.3 kilogram. Now let us refresh our mind. What do we mean by saturation pressure? Saturation pressure is the pressure at which a fluid will start changing its phase, either from liquid or to vapor, or vapor into liquid. You understand me? So for example, let's say if I have a PV diagram like this, PV diagram for water. I hope you have not forgotten this from your thermodynamics. Okay, so this line corresponds to what we call constant temperature line. Okay, constant temperature line. So assuming that we have a fluid like water, okay, whose pressure is P and temperature is given by T. Okay, temperature of the water is given by T. Now, at this particular point, the fluid is in the compressed liquid state. As you go on reducing the pressure, okay, so here the fluid initially is in the compressed liquid state, compressed liquid state. As you go on reducing the pressure, okay, so it means that the pressure will be reducing, okay, but the temperature will remain constant. You understand me? Temperature will remain constant until when the pressure reaches this state. Okay, so at this state, let's say if this is water, ordinary water, at this particular point, the temperature will be 100 degrees Celsius, and its pressure is going to be 1 atmospheric pressure, or let's say 100 kPa, kilopascal. Now, water, we all know that water boils at 100 degrees Celsius, right? But at what pressure? At 100 kilopascal. So this point corresponds to what we call the saturation pressure. So saturation pressure is the pressure at which a particular fluid will start changing phase. For example, let's say ordinarily, if I have water at 20 degrees Celsius and then 1 atmospheric pressure. If I put it on hot plate, the temperature of the water will be increasing. When it gets to 100 degrees Celsius, immediately it will start what? Boiling. So at 100 degrees Celsius, its saturation pressure is given by 100 kilopascal. So when we say saturation pressure, it is the pressure at which a fluid starts boiling or start condensation. You understand me? Okay, so now let's come back to our discussion on this. So we are saying that at 50 degrees Celsius, the saturation pressure of water is 12 points. So it means that, again, if I draw on a PV diagram like this, so it's not drawn clearly. So I have a PV diagram over here. Okay, so at 50, we are saying this is constant temperature. So this T equals to 50 degrees Celsius. Now, the saturation pressure for water at 50 degrees Celsius is given by this. So P saturation equals to 12.3 kilopascal. You understand me? So this is called saturation pressure. Saturation pressure because this is the point where we will start having this dome consists of liquid plus vapor. And this is liquid and this is superheated state. You understand me? So the moment you fall into this dome, then you are in the saturated liquid vapor mixture. And at this point, the pressure remains constant, and that pressure corresponds to what we call the saturation pressure at 50 degrees Celsius. So you see that if we take any sample of atmospheric air whose pressure is below, if the pressure is below 12.3 kilopascal, then we will be working under the superheated state. You understand? So clearly, let me draw this diagram again, like this. Okay. The moment this pressure corresponds to P saturation. P saturation. So that at any particular pressure which is below the P saturation, means pressure below this pressure, if you take a particular pressure which is below that, then it means the fluid over here will be in the superheated state or in the gaseous state. You understand me? So what we are saying over here is that at the pressure below, so this value, which value? 12.3. Water vapor can be treated as an ideal gas, even when it is saturated vapor. You understand me? So what we want to say over here is that, and as far as water is concerned, if the pressure for water is below 12 point, or the saturation pressure is below 12.3 kilopascal, then such water will be behaving as an ideal gas. So it will always be in the gaseous state. You understand me? And for this reason, we also assume that atmospheric air is also, the water vapor present in the atmosphere can also be treated as an ideal gas. You understand me? So we have two ideal gas in this case. One for the dry air component, and then the other one for the water vapor. You understand? Okay, so here now, let us see the total pressure form. We say that the atmospheric air can be treated as an ideal gas mixture, okay, whose pressure is the sum of partial pressure. So partial pressure of dry air component and partial pressure of the water vapor. So now if we take now atmospheric air, if we take, for example, atmospheric air, for example, I've told you it consists of, and now for our class, we would say like this, that atmospheric air consists of two main components. One, the dry air component, and water vapor. Okay. Now, if the pressure exerted, so I think I should draw this properly. I don't have much space. So let me see over here. Yes, assuming this is the atmospheric air, it can be drawn like this in a simple way. Okay, so this is atmospheric air. So we have atmospheric air. The atmospheric air consists of dry air and water vapor. Now, the total pressure of an atmospheric air is given by P. Now, if you divide it into two, let's assume that the pressure exerted by the dry air component is PA, and the pressure exerted by the water vapor component is PV. So it means total pressure over here, P, will be equal to the partial pressure. When we say partial pressure, it means the pressure exerted by only the dry air component plus the pressure exerted by the water vapor that is present in the atmospheric air. You understand? So like this. So, let's see. Yes, so we have the water vapor component. So, and again, the unit is in kilopascal. So from today, you should know that atmospheric air consists of two main components, partial pressure for dry air and partial pressure for water vapor. So now the enthalpy, since we have assumed that both the dry air component and water vapor are both ideal gases, so now the enthalpy of water vapor in air can be taken to be equal to the enthalpy of saturated vapor at the given temperature. So it means HV, okay, equals to Hg at the given temperature. Okay, for example, if in my room, assuming the temperature in my room is given by 70 or sorry, 27 or 23 degrees Celsius. If I ask you to determine the enthalpy of the water vapor that is present in my room, then that corresponds to HV equals to Hg at the given temperature, which is 23 degrees Celsius, like this. So, yes, 23 degrees Celsius. Okay. Now, this Hg is the saturation, the enthalpy, okay, of the saturated vapor. We have HF, as you know, in thermodynamics, and Hg. This HF is the enthalpy, specific enthalpy of saturated liquid. And this is specific enthalpy for saturated vapor. Okay, so all this will be known later on in the property table. So now the enthalpy of water vapor can be determined approximately. So either there are two options. Either we refer to the property table or calculation. We can use this calculation to determine the enthalpy for the water vapor. So means that Hg, either Hg or HV equals to Hg at a given temperature, or we can use Hg at a given temperature equals to 2501.3 plus 1.82 T. Okay, so anytime you want to find the enthalpy of atmosphere and the water vapor present in the air, you can use this equation or you can use the property table. We'll try both methods and see. Now, let us look at some classical definitions. Now, let's look at specific enthalpy. When we say specific enthalpy, what do we mean by that? You see, if I have a sample of atmospheric air, let's say sample of atmospheric air if you really understand this concept, then the air conditioning questions will be very, very easy for you. Okay, assuming we have a sample of atmospheric air in which, let's say, we have the dry air component, and then the water vapor. So this is dry air. Yes, so this is the dry air component, and this is the water vapor. Okay, so assuming the mass of dry air is given by MA, and the mass of water vapor present in the air is given by, MV. That's the mass of water vapor that is present in this atmospheric air. Okay, so this is atmospheric air. And we have separated it into two, dry air component, okay, and then we have the water vapor. You understand? So now the ratio of the mass of the water vapor divided by mass of the dry air is what we call specific humidity. Okay, so specific humidity, omega, is given by MV divided by MA. You understand? So it is the mass of water vapor that is present in a sample of atmospheric air divided by the mass of the dry air component. You understand? So very easy, very classical, easy. If you take any sample of atmospheric air, then you extract the water vapor from it. If you find the mass of the water vapor, and then you divide by the mass of the dry air component, that gives us what we call the specific humidity. And specific humidity can also be expressed in this form. It can also be expressed in this form. So maybe we can, let's see over here. Let's see. Okay. Yes, so now let us continue the derivation. Okay, we have defined that mass of, specific humidity is given by this. Now, but we have also mentioned that this omega can be also written as 0.622 PV divided by P minus PV. Okay, so let's see. Now, from ideal gas, okay, we have PV, okay, and then V equals to MV RV times temperature. Okay, assuming we have a certain sample of atmospheric air, and this atmospheric air has a certain mass of MV and a certain mass of MA. Okay, so since both fluid are ideal gas, so then we can express them in terms of this, that PV, now the total volume of the system is given by V. So this volume, the volume occupied by the dry air is the same as the volume occupied by the water vapor. So the V remains the same. Similarly, the temperature of both is going to be the same. Temperature for the dry, because if you are sitting in your room now and you measure the temp, you have a thermometer with you. The thermometer will be reading maybe 22 degrees Celsius. This 22 degrees Celsius is for both the dry air component and then the water vapor. Okay, so temperature remains the same. The volume remains the same, but the mass and then the masses will be different. You understand? So that's why I put, and then the pressure exerted by the water vapor is given by PV. Pressure exerted by the dry air component is PA. So now we will have the ideal gas component for the dry air is given by PA. V equals to MA times R. You know, this R is the ideal gas constant times temperature. Okay, so now if we divide these two equations, let's say this equation 1, this equation 2, if we divide one by the other, so we will have a situation like this, that this, or we can have MV divided by MA is equal to, this gives me PV times volume divided by RV. This is the ideal gas constant for water vapor times temperature, all divided by PA times V, all divided by RA times temperature. Okay, so certain terms will cancel out from this equation. Okay, V is common over here. Temperature is common to both sides over here. Okay, and then we will have a situation like this. This now becomes equals to, so now this becomes equals to, if we cancel the like terms, we will have PV divided by PA times RA divided by R what? V. Now, if you look into the property table, the ratio of the ideal gas constant for air and the ideal gas constant for water, the ratio will give us 0.622. Okay, so that's why we say that the specific humidity, MV, omega equals to, so this is also, so omega equals to MV divided by MA. This equals to PV divided by PA times what? 0.622. Okay, so but we know that the total pressure present in the air equals to PA plus what? PV. So now if I'm looking for PV, so PV gives me equals to P minus PA. Or in other words, let's say if I want to express PA, PA will give me, so I'll say PA equals to P minus PV. So it means omega can be expressed in terms of PV, okay, all divided by P minus PV times 0.622. Okay, so this is the derivation for that equation. Yes, derivation for this equation. That's the specific humidity. Okay. Yes, so that's the derivation for this particular equation. Okay. So now let us move on. Now we come to relative humidity. Definition for, now we know specific humidity. Now let us look at the definition for relative humidity. So relative humidity is defined in a similar fashion. So let's say again, if I have a sample of atmospheric air, okay? So atmospheric air. Okay, so assuming this is a sample of atmospheric air, this atmospheric air can be again split into two. We have the dry air component, and then we have the water vapor. Okay. Or let me see, I think instead, yes, so, and this is the dry air component. Or let me define it in this way instead. I think, let me define it in this way instead. Assuming we have a sample of atmospheric air like this, in which the pressure exerted by the water is given by this. And then the pressure exerted by the dry air is this. So this is the sample. Sample of atmospheric air, yes. So at this particular situation, let again the mass also, the mass of the water vapor to be this, and the mass of the dry air to be equal to MA. Now, if I introduce some moisture, if I continue to introduce some moisture into this system, so it means I'm adding some more water. Okay, so if I add more water into this condition or this container, so what will happen to MV? MV is going to what? Increase, right? But the MA will remain the same. MA will not change. Mass of dry air will remain the same. It is the MA, MV which will be increased. You can think of humidification, humidifier. These days, we have a lot of humidifiers in the shop. If you go to Giant, you want to buy humidifier, they will give you. You just place it in your room, then it will be spraying the water into the atmosphere. So then the amount of water vapor present in the air will be what? Increase in this way. You understand me? So now, if you continue increasing the amount of water vapor in the air, it will reach a stage where the air can no longer absorb the excess water. At that particular state, we say that the atmospheric air is at the saturated state. You understand me? So that at the saturated state, the MV changes to what we call mg. You understand me? So like this. So at a saturated state, and then at saturated state, sorry, at saturated state, we'll have a situation like this, where this MV changes to, sorry, yes, so this MV changes to mg, okay? And then the PV also, PV changes to PG, because that's the saturation pressure. But MA and PA remains the same. MA, because mass of dry air and the pressure for the dry air component does not change. So at the saturated state, the ratio of the mass of the moisture that is present, okay, at the initial state. You see, this MV, the mass of MV divided by the mass at the saturated state, divided by the mass at the saturated state. This is what we call relative humidity. Okay, and it can be also expressed in terms of its pressure. Okay, the partial pressure of the water vapor divided by the partial pressure at the saturated state. So very, very important for you to know this. It's very, very, very important. Okay, that you should know these things, these two things. Okay, so now, yes, so where the saturation pressure, PG, is given by P saturation at a given temperature. You understand? So today now we have known two equations, very important equation. Omega is given by MV divided by MA, and phi, that's the relative humidity, is the ratio of the amount of water vapor that is present in a sample of air divided by the maximum amount of water that the air can hold. Okay, so it can be expressed also in terms of the pressure like this. Okay, so consequently, we can also derive other related equations for omega and phi like this. Okay, so we will not go into this derivation, just need to know them. Okay, so now let us see the enthalpy of atmospheric air can be expressed as the enthalpy, the sum of the enthalpy of the dry air component plus the sum plus the enthalpy of the water vapor. Okay, so like this, you have, let's say, enthalpy for atmospheric air. It can be divided into two, enthalpy for dry air component, and then we have the enthalpy for what? The water vapor. Okay, so now we can express it in this. Now, bring your mind over here. The specific enthalpy is absolute enthalpy divided by mass. Similarly, specific volume is given by absolute volume per unit mass. You understand me? So, this is not a new thing. This is a recapture of what you did in your thermodynamics. You understand me? So, now we can express these two equations like this, that we can define the enthalpy. Yes, so like this. So the enthalpy for dry air component is the absolute enthalpy divided by mass of dry air. So we can say that we can say that, yes, absolute enthalpy equals to HA times MA. Similarly, HV equals to HV times MV in this way. So we can substitute into these two equations like this. Okay, so now if we divide through by MA, so now the equation reduces to this form. So watch out carefully. Watch out carefully. So I have over here, let's see. Yes, so we have H equals to MA, or let me see, I'll use a different technique. So if I divide this by MA, and I divide this also by MA, now I divide this also by MA. Okay, so now this becomes H, because what is H? H is simply enthalpy divided by the mass. Okay, absolute enthalpy divided by the mass. So now, but mass of the dry air, of course, mass of the dry air. So now, this gives me MA will cancel MA. I'll have HA plus what? Now, MV divided by MA, this equals to omega. So this gives me omega times HV. Okay, so anytime we are interested in determining the enthalpy of atmospheric air, whenever they ask you, determine the enthalpy of an atmospheric air, then this is the equation you should use. So enthalpy of atmospheric air consists of the dry air, enthalpy of the dry air, plus the specific humidity times the enthalpy of the water vapor. You understand? So very, very important. So now this is the equation which we have just derived. Okay, later I will come to this particular equation. Sorry, question. Okay, we will discuss these questions later on. Now, let us look at adiabatic saturation. Okay, so the word adiabatic means it's a thermodynamic system in which no heat is allowed to flow in and out of the system, highly insulated system like this. Okay, so now assuming that we have a very, 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 very infinitely long tube, okay, and then we allow, let's say, atmospheric air to pass through. Okay, so atmospheric air we allow atmospheric air to pass through. So initial properties, so this is called unsaturated air. These are the properties of the air: temperature T1, omega 1, phi 1, that's the specific relative humidity 1, all these things like that. So now, as the air flows across this water, what will happen? The water will be absorbing some of the atmospheric air will have the opportunity to be absorbing some of the moisture from the water. You understand me? So more water vapor will be evaporated into the air. So by the time it comes out at state 2, so then there's relative humidity. The humidity will be very, very high. So maybe 100% relative humidity. You understand? So very, very important. So here, this is the temperature of the water which you are putting inside a tube. And on a TS diagram, on a TS diagram, this line is called constant pressure line. It's a constant pressure line. Okay, and this is the saturated liquid line is this, and saturated vapor line is this. So if the sample of atmospheric air initially that enters the system is this, okay, at state 1, the moment the fluid starts flowing across the water, it means its temperature will be reducing gradually until eventually it will start forming what we call dew. Dew means that condensation. You understand me? Condensation. So this particular point, the temperature that corresponds to this point is called the saturated or the dew point temperature. You understand me? Or the saturation temperature. Okay. So now, and the mass of dry air, if you consider the mass balance of the dry air in this particular device, okay, so we have a certain sample of atmospheric air entering, whose mass of dry air is this, mass of water vapor is this. Okay. And then at the exit, we have the mass of, again, dry air component, mass of water vapor. So let's say this is MA1, MA2. So as far as the mass of dry air is concerned, mass of dry air remains the same. It doesn't change. You see, whenever you are putting some moisture or water vapor into the atmosphere, the mass of the dry air remains constant. Only the amount of moisture, the amount of water vapor increases gradually like that. So it is the MA is never affected in any case. So that's why we have mass of dry air at state 1 equals to mass of dry air at state 2 equals to mass of dry air at state 3. You understand me? So now if you want to find the mass balance, okay, mass flow rate of the water vapor in the air, okay, so if you consider the mass balance or mass flow rate of water of vapor in the air increases by equal amount of the rate of evaporation. And it is true. You see, if we look back into our diagram, okay, so assuming the mass of the water vapor MV over here equals to, let's see over here. Yes, MW1. This equals to MW1. And this equals to MW2. Okay? So, and this is the mass of the water. So we say MF. So as the fluid passes through this tube, the mass of MW1 increases by this amount, MF. So it implies that MW2 will be equal to MF plus MW1. You understand me? So that's the mass balance for the water vapor. Okay, so yeah. So now we can rearrange this equation like this and say that we have already told that MW1 equals to MV1. Okay, so by definition, omega 1 equals to MV1 divided by MA1. So I can rewrite this equation and say that MV1 equals to omega 1 times what? MA1. Similarly, I can write MV2 equals to omega 2 times what? MA2. So whenever I see MV1, MV2, I'll put these parameters. And that's what we have done over here. So MF remains the same. Okay? Like this. So eventually, the mass flow rate of the water, which is evaporated, is given by this. Okay? So sometimes you can be asked to calculate this particular mass flow rate of water. Similarly, if you want to look at the energy balance in the system, okay, so the energy, the total amount of energy entering should be equal to total amount of energy that is exiting the system. Okay, so we will have, but this energy is given by, so you see again here, so here we have at this state 1, the fluid has well-defined enthalpy H1. And at this state 2, the fluid has enthalpy H2. Okay. And mass flow rate of the dry air is MA1. Here we have MA2, like this. So, and for energy balance, we have the energy entering at state 1 given by E1. The energy leaving at state 2 is given by E2. And the energy of the water that is entering from here is given by EW. Okay? So that the total amount of energy entry should be equal to the total amount of energy which is leaving. So we will have E1 plus EW1, sorry, EW equals to E2. You understand? So now we need to define this E1 and E2. E1 is nothing, it is the mass of the dry air times the enthalpy of the dry air. You understand? So that's what we have over here. Mass of the dry air times the enthalpy of the dry air. Plus, again, MF we know already, times HF. Okay? And then this should be equal to the whole of this. All right. So now, if we rearrange the equation, we can express it in terms of this, or in terms of this, or in terms of the omega 1 and omega 2. So I'm not going to derive all this, so it will be a waste of time. Okay, so now we have, in air conditioning application, there are two types of temperatures. We have the dry bulb temperature and then the wet bulb temperature. Okay, so dry bulb temperature is the temperature, if you have a thermometer in your house, okay, the temperature which will be read by that thermometer is called the dry bulb temperature. However, but on the other hand, the wet bulb temperature is read from a wet bulb or a wet thermometer, which is an ordinary liquid in gas thermometer, whose bulb is enclosed by a wick, moistened with what? With water. You understand? So you see over here, these are the two common types of thermometers. We have the wet bulb thermometer. Here the wick, there is a wick which is bounded by this particular tube. Okay? So here, again, this is the dry bulb temperature. So the temperature read by the dry bulb temperature is always higher than the wet bulb temperature, like this. Okay? So this another device which is used to measure the temperature. Okay, so it's called aspirating psychrometer. Okay, so again, we will come to these questions later on. Now, next very important area is the psychometric chart. Psychometric chart, we will be using it in air conditioning application. Okay, there is no doubt. It is a chart which is designed to be used to measure the properties of atmospheric air. So the psychometric chart is a chart which is designed, okay, to determine the properties of atmospheric air. Okay, now it has what we call the, let's see, a vertical axis. And this vertical axis is called the specific humidity axis. So that is the omega axis. Okay, that's the specific humidity axis. You see over here, this is the humidity ratio, or specific humidity is given by this. And then we have the dry bulb temperature. This is the dry bulb temperature. Okay, so now apart from this, we have also the enthalpy. The enthalpy of atmospheric air is given by this. Okay, so these lines, this corresponds to enthalpy of atmospheric air. And we have relative humidity. Relative humidity, 100% relative humidity belongs to this line. You see, this particular line. And it continued to decrease. So this is 100, 90, 80, 70. It goes on like this. So these are lines of constant relative humidity. And then we have also the wet bulb temperature. This is the wet bulb temperature. Okay. like this. And also we have the specific volume of the atmospheric air is given by this. So later when you start looking at questions, you will see. Yes, so these are the summary. You have the specific humidity on the vertical axis, omega. You have the dry bulb temperature like this, and wet bulb temperature, enthalpy, specific volume, and the relative humidity is given by this. Now, in air conditioning applications, I've told that we have simple heating, simple cooling, humidification, and dehumidification. So now we're going to look at these areas of air conditioning application. Okay. So now, in various air conditioning applications, we normally refer to the psychometric chart. So a psychometric chart can simply be drawn like this. Okay. This is the dry bulb temperature. This is omega. And then we have the relative humidity, which is given by this. Okay. So whenever we have a heating situation means temperature is increasing. Let's say from this reference point all the way. And this is called simple heating. And for a cooling means temperature is reducing. And this is referred to as simple cooling. And if we have heating and humidification, okay, or let's say if we have humidification, okay, means we are adding only moisture to the atmospheric air. So we have humidification. If we remove the moisture, then we'll have dehumidification. Here we can have heating and humidification. We have cooling and dehumidification this way. So these are the various techniques for describing the air conditioning applications. Now, in simple heating situation, we normally have a heater, okay, embedded in the air conditioning duct. So let's say we have a very long air conditioning duct, And then in the middle of the duct, we put a heater. Well, what is the job of the heater? To transfer some amount of heat. In other words, to raise the temperature of the air conditioned air. Okay? So now at the exit of this air conditioning, what happened to the fluid? Okay? So here we have, let's say, let me draw the psychometric chart for this. If you draw the psychometric chart for this simple heating, like this. So let's say this is state 1 of our fluid. So for simple heating, it means it goes horizontal. Temperature, this is dry bulb temperature, this is omega. Now this will be state 2. You understand me? So now, at the initial entry, so we have the atmospheric air is entering at this, and then it leaves at this particular state. You understand? So that's the exit. So, but by the time it comes out, what will be the temperature of the air? T2 will be greater than T1. You understand me? So here, T2 will be greater than T1 because of what? Heating situation. But what will be the omega? So here we have omega 1, we have omega 2. It is horizontal. It remains the same. It does not change. So omega 1 equals to omega 2. And we have the relative humidity over here. This is phi1, and this is phi2. And relative humidity number 1 will be greater than relative humidity number 2. So this is how to describe this situation. Okay. Now, for a simple cooling, it is the opposite of simple heating. So in simple cooling, we have initial temperature is this, number 1. So the fluid is cooled up to number 2, like this. Okay. So for both cases, omega 1 will be the same as omega 2. And T2 will be less than T1. What about phi? Omega 1 is less than, phi1 is less than phi2. So this is relative humidity number 1. Number 2 is this. Okay. So you observe carefully that over here, the relative humidity at state 2 will be greater than relative humidity at state 1. Okay, so now we are almost done. Now we are looking at heating with humidification. So how do we conceive this? In a heating and humidification, we simply have atmospheric air entering the duct. So it is heated. We give some Q in like this. And after state 2, we bring in some moisture, water vapor. So water is sprayed into the air. So it means that the moisture content increases. Okay, the relative humidity, the specific humidity increases. You understand me? So like this. So if you sketch, maybe by the time we start solving questions on this area, it will be clear. So I'll have a situation like this. Yes, so simple heating means we move from state 1 all the way to state 2. And then humidification. Humidification means it moves up. The line moves up to state 3. Okay, so here, similarly, omega 1 equals to omega 2, but phi 1 is greater than phi 2. And then we have T2 is greater than T1. Okay. Now, at the exit at state 3, we will have omega 3, because this is omega, this is temperature. Okay, omega 3 is greater than omega 2. Okay, and then other parameters like this. Okay, so in simple cooling with dehumidification, also we will have a situation like this. Okay. All right. So I have told you that this line corresponds to 100% relative humidity. 100% relative humidity means the dew has started forming. So let's say if we have the air conditioned air to be at this state, let's say, let me change the color. So initially the air is at state 1. So now it enters this air conditioned duct. Cooling means that we are removing the heat. Cooling. Okay, temperature is reducing, means Q out. So means temperature is reducing. So it will move to the left. So continues to move until eventually when there will be see. Yes, so it continues until eventually when it touches this line. And this line, then it means that there will be condensation taking place. So this is the condensation. The condensation means there will be, because of 100% relative humidity. So continue to cool down, the temperature will reduce even at a particular state. Okay? So this will be state 1. And then final state, let's say maybe this is state 2, like this. Okay, so the temperature is decreasing. There will be water vapor that is, there will be moisture due to condensation. Okay, so then these parameters, yes, omega 1 is greater than omega 2. See, this is the line for omega. Omega 1 is greater than omega 2, this is state 2. And similarly, phi number 2 is greater than phi number 1. Okay, these are the important things we need to know related to this. Okay, so let me see. I will stop over here. In the next class, I'll discuss the adiabatic mixing airstream, and then the rest of the class will be solving questions. Okay, so let me know if there is any question. Is there any question from anybody? Yes, any questions so far? So, and since there is no question, then